Now let us complete this red black tree with this last topic, that is a deletion of red black tree, right? Deletion of red black tree. So it is so much simple, and you need to remember some cases. That's it. So let us go through this. So first of all, you need to delete. Imagine you need to delete a node. Okay, that node is red. So you need to delete a node, and that node is red. So what you will do? You check that. First of all, you check whether that node is leaf or not, right? If it is leaf red node, then just delete it. Just delete it. So here, imagine it again. In this example, it is a node is red and it is a leaf. I will delete it. Whether it will change any breaks, any condition that we have discussed in the previous lectures, in that is in introduction of AVL tree, it is a red black tree. No. So now imagine the node that I need to delete is again red node, that is B. In this case here I need to delete B. So it is a red node. Okay, then check whether it is a leaf node or not. Here B is what? It is not a leaf node. So what you will do, bring its child to its position. That's it. You can simply delete. There is no problem here. Bring D at this position. So that's it. There is no problem. And let me talk about the third condition. Third condition is I need to delete a black node, that is D in this case. So what I need to do is first check. First I'm going to check. What you are going to check? I'm going to check what is the sibling of D. Since D I need to delete and D is black node. So check its sibling. Its sibling is S. What is it? It is a red node. So rotate. This simply what you need to do is simply delete this D. So what you get? It is an unbalanced tree, right? So how do you make it as a balance? Simple. You will simply do left rotation, or RR rotation, or zigzag rotation. So is it? So we can use any word here. So if I do rotation, again S will be what? It is a root node. It should be black. Then P and A will be what? P here and A is here. They are red. So this is what I am going to do. Now let me talk about the fourth case. I need to delete D. Yeah, you need to delete D. It is a black. So what you have done in previous step, you have checked the sibling, right? So check the sibling. So it is also black. So if it was a red, you rotated. If it is black, it is black. Check its child. Now, since it is not red, that you can't rotate. Simply rotate. You check its child. So at least you should have a one red child. If you have at least a one red child, then rotate again. Again you rotate. Just perform rotation. So again I will remove. It will become imbalanced. So again, if you rotate here, right first, then left second, it is nothing but RL rotation that we have discussed in AVL tree. And again, it can be called zigzag rotation, right, in AVL tree, that is in red black tree. So I will do that. So here what I am going to get is S will go here, A will come here. So A will be what? Red. A will be what? Red. And P will be what? Will come here. S will what? It will come here. So if A is right, A is a root node, you can change it to black. But if it is a some subtree of it is some a problem in a bigger like subtree, so it is not necessary to change it to black unless below you have again another red. In that case you can change it to black, right? You can definitely, you need to change it to black. Some red node, I am talking about sub problem. It is just like a sub problem. Imagine this as a sub problem. So again in this case also, don't consider it as a total problem. It is some sub problem, some part of the sub problem. So that is why my P is, I took P here. So fifth case is this. Check D. You need to delete D, your objective. So it is a black node. So check its sibling. What it is a black node. If it is red, then rotate. If it is black and has a at least one red node, then you rotate. And as if it is red, again rotate. So if you need to delete D and its sibling is red, rotate. If its sibling is black and that black node has at least one red node, then again rotate. Now here there is no red node. Then what you will do? Then you will do recolorization. Recolorization means you will change the color of the node that you are deleting, right? Its parent and its sibling. Then means opposite the color. Like P was red, make it as a black. Sibling S was black, make it as a red. Then take A and B here. See, is it a balanced tree? No, it is balanced. It is not balanced tree, but it is one of the subtree, right? I am not talking about tree at all. I am talking about some subtree. So don't worry about balance. Maybe there is some nodes there, and here there is something, and it may balance. It may become balanced. So don't worry about it. Now, this is a 6 case. You can take it as 6 case, because here I am going to talk about how to remove the root node data. Again, I will mention root node data. Why? I will explain you in this video itself. But again, I am going to cover most of the topics here. Means all other upper cases that I discussed, I am going to cover this in this video. So it can be taken as a 6 case, and it is actually a mixture of all the cases you can take. Now, what is this? Here I need to delete 90. Can I delete 90? Yes, you can. Simply delete. It is just a what? Black. It is a red tree, right? Red node, right? Simply delete. There is no problem. So again, but I will not delete it. And this is 100. Again, I did some mistake here. It should be 100, right? Because it is not that it should be 100, right? I took it. It was 90 here. So here also 90. As I said, it is like binary search tree. There should be no duplicate element in binary search tree. That is one condition. So by mistakenly I took 90 here also. Here I took 90. So I have recorrected that one. Now I need to delete what? Let me delete 100. Okay, delete 100. Check out whether it is a red or black. It is a black. So check out it as a child. Yes, it has a child. It has children. Right? But you can't replace this whole children at this place. So what you will do is you will apply 6th case that I was talking. So it is a root node, right? Consider it is not a root node. Consider it as some root node. So in 6th case was what? How to delete the root data. So consider it as a root node, right? Now, this root node has to be replaced by its in order predecessor. Here in order predecessor is 90, or in order successor. Here 110 is the in order successor. You know, in order and post order and pre-order, everything you know. So in order means 90, and in order successor is 110. So let me replace it with 90. Here also, here only I will I will erase, because I don't need to write it again. So I will simply remove this 90. I will put in this place. Let us see if it will work or not. Yes, it has worked. So it is satisfying normal binary search tree, and at the same time, see, I have removed red node, so there is no problem for me. Again, now I got the result that I simply removed this and placed it this here. And again, I said, right, I am not deleting root node. I will always be deleting a leaf node or a node with a single child. Here 100, I had 2 child. So I am not deleting that position. The 100 position was what? This one. Now also it is there only. What I deleted was 100. Which position I deleted? I deleted 90th position. 90 was here, right? So its position was here. So what is 90? It is a leaf node. I can delete. I will delete actually leaf node and node with a single check. That is what the one of the thing that you need to remember. Okay, now let us move forward. I need to delete 1 on 0. Check whether it is a black tree. Yeah, it is black. You will see sibling, right? So don't do that mistake again. I said this one for you here. If it is black, see its sibling. You can do that, there is no problem. See here, what I deleted was leaf red node, sorry, leaf black node. Is it a leaf black node? Never. It is not a leaf black node. So take it as a root. Imagine this as a root. It is just a root. Now what? Now it is a root, right? So I will replace it with successor now, in order successor. Right? In order successor is 120. It is red. So don't worry. Simply replace it. So I will remove everything. Should I make it as a red node here again? No. It was black and let it be black. If you made it as red, that is your problem, because again red conflict will become. So 120 which was there in a red node, I brought it this here. So imagine I need to delete, like I need to delete 80. How can you delete 80? It is 80. It is a leaf black node. Look its sibling. So it is 120. Is it a black? Yes, it is black. So check its child. Their child is no null, but we know null nodes are black. So it has no, at least there is no, not even a single red child. So what is the thing that you need to do? Recolorization. Recoloring, that is recoloring. Means I am going to delete this first of all, 80. So change 90s, its parents color and sibling color to opposite. 90 was what? Red. Now I will make it as a black. 120 was black. I will make it as a red. So I will make this as a red. 120, this is 120. Sorry, 120. 90 was what? Black. So red. Now I'll make it as a black. So let me write clearly. This is 20, this is 120. So sorry, this is 90, this is 120. So it is all. Now they have said you to make, again, one topic is, I think, like you can, like what we have done here, let us see again. So this was my condition, right? I wanted to delete 80. If you delete 80 here, it will become null. Actually, it will become double darkness. There will be double darkness here. It is not just a darkness, it is a double darkness. Why I said it is double darkness? Because red node tree should have black, number of black should be maintained, red number of black nodes should be maintained. If I make this as a double black, then consider it as a 2 black nodes. So 2 plus 1 was what? 3. So this will satisfy, and this will satisfy the condition. But again, after that you need to do the same thing, right? If you consider this as a double black, imagine this, you consider it as a double black, you need to remove this double black. It is not an ideal condition. It is just to make a tree, all the 6 conditions that we discussed in the introduction class, to make it as a like satisfying, we made this double black, but it is not a double black. Again, see, it is a black. See its sibling. See 120, no childs are red. So recolorize. So I will again do the same thing. I have done nothing here. I did the same thing. I used a new keyword called as the normal word. That is normal word. It is not a keyword. So I have made that is the double darkness. So this is 90. I have deleted that. So I got 120 here. So now imagine I need to delete 120. Can you delete 120? Obviously it is a red node with, it is a leaf node, you delete it. Now I need to delete 90, right? I need to delete 90. So again, if I delete this one, it will become double darkness. There will be double darkness here. So how to remove this double darkness? See its sibling. It is what? 40. Okay, 40. Then what you will do? You can actually rotate. Which rotation you will apply? That is left to, like in Abel tree we have discussed, right? So 40 will become where? It will come here. So 40 will come here to the root position. 70 will be there only. 70 will be here. 70 will be here, and 40 will be here, and 40, right? 40 become root node, and it is connected to what, 20. So 20 will come here. Then 20 has two red nodes, that is 10, and this is 30. And you know this. Now after what I am doing, this you know already. Here you have, for 40 you need to take care of its child, right? 50 and 60. 50, I already said you, if there is a thread like this and there is a stick like this, if you pull here, what will happen? That will stick will come here. So similarly 50 is like that, it should come here, but I will do something here. I will take it as a red. So I should take it as a red. That is 50. Now 60, normally this is also we have, right? And we will make it as a right child of 50. So it can be right child of 60, and it can't be red. Again, why it can't be red? Because there will be conflict. So let us see about the conflict afterwards. Let us make it a 60. Now what? Let me erase this thing also. Now there is a red conflict. So what you will do? You will rotate, right? As you have discussed already, I think in insertion we have discussed, if there is a red conflict, what I am going to do is, as I discussed, if you come up here, we have discussed this thing. So this is a red conflict. I am getting red conflict. Then rotate it, right? You need to just rotate. Here my condition is just similar to, see here red is exists in this condition. So here we have did like this, right? So similarly I will do in different position, different angle. That's it. Angle was changed. So my result would be what? My result would be, and again 40 is what, red, but it is a root node. I will change it. We'll change it to what, 40 as a root node, that I have discussed here. That if it is a root node, you need to change. So 70. Then this is what, normally 10, 20. Yeah, sorry, it should be not 70, right? Should be not 7. This one shouldn't be 70. So it will come here. So 50 will go down. 60 will come here. 60 will act as a what? Root node now. Sorry, not root node, like a parent node. So 60 should come here. 60 should come here. Then again here we have what? Here we have, this is I think 50, and this is what? 70. So this is what about the deletion in red black tree. Then we are going to next topic, that is binary heap. So if you have any doubt, you can check out this playlist, that is tree.